Hey guys, this is Red Pig. Today I want to tell you my solution of problem 6 in 2018 IMO. So let's go through the problem together. We are given a convex quadrilateral ABCD satisfies AB times CD equals to BC times DA. And there is a point X lies inside ABCD such that the angle XAB matches the angle XCD. And furthermore, the angle XBC matches the angle XDA. So in this figure, the blue angles matches each other and the red angles as well. And the problem is to show that the angle BXA is the complement of the angle CXD. So the configuration of the figure is quite simple. However, from the first glimpse, it is not clear how we can use these assumptions. In particular, this AB times CD equals to BC times DA condition is quite unnatural. So let's forget it for a moment and try to use these angle equalities to derive some useful properties. So first, we construct the circumcircle of the triangle ABX, and we denote P as the intersection of this circle and the line BD. So P is the second intersection of the circle ABX and the line BD. And we are going to prove that P also lies on the circumcircle of triangle CXD. So P is also on the circle CXD. So to see it, we follow a simple angle tracing argument. So indeed, since ABXP is on the same circle, we have the angle BAX is equals to the angle BPX here. And moreover, by assumption, we have BAX is the same as XCD. So we have the angle BPX equals to angle XCD, which implies P is on the circle XCD. Then next, we prove the following relationship between angles. So we want to prove that the angle BAC plus the angle BCA equals to the angle PAD plus the angle PCD. So indeed, later we can see that the angle BAC is equals to the angle PAD and the angle BCA is equals to the angle PCD. But for the moment, we don't know how to prove it. But we can prove instead that the sum of these two angles are equal to each other. Let's call this equation star. To prove it, we follow another angle tracing argument. So we remark the following fact. So the angle BAC plus the angle BCA is equals to the angle ABE here, the pink angle. So now we add another angle XBC to it. So this means that this equals to the pink angle ABE plus the angle XBC, the red angle XBC. And this is the complement of the angle ABX. And since ABXP are on the same circle, the complement of ABX is the same as the angle APX, which is the green angle here. Now we decompose this green angle as the sum of the red angle here, blue angle here, and the orange angle here. So indeed, APX is the sum of the angle PAD plus the angle ADX plus the angle PXD. And since P is also on the circle CXD, so the angle PXD is equals to the angle PCD. So this is the sum of the angle PAD plus the angle ADX plus the angle PCD. And now by the assumption that XBC equals to the angle XDA, so these two angles cancels. And this is exactly the star we want to prove. So now let's reformulate the statement that we want to prove with respect to the angles around the point P. So since ABXP is concyclic, we have that the angle BXA equals to the angle BPA. And similarly, since CXDP is concyclic, we have that the angle DXC equals to the angle DPC. So now it is sufficient to prove that this angle APB plus this angle CPD equals to 180 degrees, which is equivalent to prove that BP is a bisection of this angle APC. So if BP bisect the angle APC, then APB equals to BPC, which is the complement of the angle CPD, and that's what we want to prove. To summarize, we have transformed our problem into another problem which is independent of the point X. So the problem is the following. We define a point P on the segment BD such that this relationship star holds. And indeed, this relationship star uniquely determines the point P. And what we want to prove is that this line BP bisects the angle APC. And remember that so far we have not used this condition AB times CD equals to BC times DA. And here is how it comes to play, and let's see how we use it. So let me rewrite this equation in a different way. Indeed, we have AB over AD equals to CB over CD. Let's call this ratio K. If you are familiar with the harmonic points, then you may immediately recognize some connection. If you are not, let me explain it to you. Indeed, we should think that B and D to be two fixed points, and we are interested in the following set, which are the points y such that yb over yd equals to k. So yb over yd has the same ratio as ab over ad and cb over cd. So a and c belongs to this set. In particular, if k is not equals to 1, then this set defines a circle. And it has a name which is called the Apollonius circle. So Apollonius like this, circle of BD. And when k equals to 1, this problem becomes relatively simple. I will let you guys figure it out. So let's consider the case k different than 1. Call O the center of this circle. Then we have that O lies on the line BD. Moreover, O has these remarkable properties that OB times OD equals to R squared, which is the radius of this Apollonius circle. In particular, since A and C lies on the circle, we have that this equals to OA squared and also equals to OC squared. So I will prove this relationship later, but let's believe me and see how we can conclude from it. So let's call it star star. So from star star, we have that OB times OD equals to OA squared. This implies that the triangle OBA is similar to the triangle OAD. In particular, this angle OAB equals to the angle ODA. Similarly, we have that the triangle OBC is similar to the triangle OCD. And then we have OCB, the angle OCB, this orange angle equals to this one. the angle ODC. Then now if you remember how we define the point P, we have this relationship that the sum of the angle BAC plus the angle BCA equals to the angle PAD plus the angle PCD. Then using these three equations together, we can easily prove that the angle APC plus the angle AOC is 180 degrees. And this implies that the 4-point AOCP are concyclic. In particular, we have that the angle APO here, the angle here is equals to the angle ACO. And since OA equals to OC, we have ACO equals to CAO, so equals to CAO. And this is equals to the angle OPC. So this concludes our proof because it means BP bisects the angle APC, which is the desired property we want to show. To summarize, we have first removed the dependency on the point X, and then use this remarkable relationship on the Apollonius circle or harmonic points. Now let me finally show you how to prove star-star, which I remains behind during my discussion. So the claim that I leave behind is the following. We consider this set Y such that YB over YD equals to K. We want to first prove that this set is a circle if K is different from 1. Then we want to show that the center O of this circle satisfies this relationship star-star, which is OB times OD equals to the radius square R square, which is OA square or OC square. So let's proving first that this set is a circle. Indeed, since K is different than 1, we can find 2 points E and F on the line BD such that it belongs to this set. So E and F are on the line BD such that EB over ED is equals to K, which is also FB over FD. Now take any point Y belongs to this set. Let's just take the point A for example. Then we have BAB over AD is equals to K, which is the same as EB over ED. And by the theorem of bisection angles, this means that AE bisects the angle BAD. So this means that EA bisects the angle BAD. With a similar argument, we can show that FA is indeed the exterior bisection of the same angle. So bisection of the same angle. And this means that FAE is a 90-degree angle. So the angle FAE is 90 degrees, which means A lies on the circle of diameter EF. Then O, the center of the circle, is the midpoint of EF. So now we are in shape to prove this final property star-star by remarking that O is the midpoint of EF. Indeed, we rewrite the ratio EB over ED as the following. So EB is OE minus OB, so which is R minus OB, and ED is here, is OD minus R, so OD minus R. And we do the same thing for FB over FD, which is FB is R plus OB, and FD here is R plus OD. So if we put them together, we have R minus OB over OD minus R equals to R plus OB over R plus OD. And if we rearrange this equation, it gives us exactly R squared equals to OB times OD, and this is the desired star star. So this is the end of our proof. I know that the proof is very long, and in particular, if you're not familiar with harmonic point or Apollonius circle, this can be quite difficult to digest. So you may need a bit more time to understand these concepts. So here I show you a simple animation by moving the point y around, keeping that yb over yd is a constant. And you can see that this forms a circle, which is the Apollonius circle with back to B and D. Hope you enjoyed the video. If you like it, don't forget to subscribe my channel. I will continue uploading interesting math problems. Bye bye.